So we are looking at geometrical meaning of angular momentum. It's a peculiar thing that we're looking at. But what does it do? Well, this is useful for understanding and deriving Kepler's second law. So what exactly are we doing here? See, the area set by the line connecting the axis of rotation and the particle. Let me show this. The discussion should start with what exactly we are talking about. So we have our x, y, and z axis. And we have a particle at a point. And from the origin to that point, we have r, vector r, connecting them. Now, if we have it moving to a new position q, and we have this, the path. So it has moved from P to Q, right? So let me, now, what is the area swept? So if it's rotating this way, okay, if it's rotating, what is this? Anti-clockwise direction. The area that the line has covered is this. Do you guys agree? Simple thing. Think about it. Is this the area covered by this line? Right? Is it not? So this area and the, where is it? And your angular momentum, where is it? The angle set by the line connecting axis of rotation, the particle, has a certain relationship between angular momentum and itself. I mistyped this. It's supposed to be itself. Itself as an area. And this is what we are trying to explore. And I just told the uses. The use of this idea, we will be seeing that in Kepler's second law. Okay. So that's that. Now we have x, y, and z, right? So let me start by talking about, let me write it here itself. Let's talk about the diagram, the situation. We're considering a particle of mass m rotating along xy plane about the origin O. Let the position vector be r at time t and be r plus delta r at time t plus delta t. Okay, so I'm calling this as r plus delta r. So what will be my displacement PQ? Therefore, PQ will be what? The difference between these two. Sorry, where is it? Yeah, this and this. Correct. This expression and this expression. So basically, this will result in delta R. So that's your displacement. So actually, let me write it clearly. Therefore, the displacement will be delta R. Okay, so displacement is this. See, the thing is, we are considering delta t, a very small time. To be honest, it is an arc. You know, PQ is supposed to be an arc, but we are considering it to be almost approximately equal to delta R, which is a line connecting PQ, a line segment PQ. Reason being delta t is small. Then let's consider V be the velocity at P, right? It should have a velocity at P, and theta be the angle. I hope I can fit between R and V. Okay, so basically, if I extend this, Let me write it over here with this color. If I extend this, don't take it as perpendicular, that is theta. Okay, so that would be theta. So let me make it clear with this actually. So basically you'll end up with this. Let me change the color again. So you have R, okay, just a second. You have R, right? I'm extending R, I'll do that later. Then you have delta R. And then you have your extended line over here. Okay, so this is R and this is our delta R. Delta R and V will be in the same direction. So this is basically theta. Okay. And if I join this is nothing but as per our vector addition, R plus delta R. This angle will be 180 degree minus theta. Now, since we are talking about area, how do you figure out the area? Base into height, half into base into height. And how do you find this length? Sorry, I have to do a bit of arrow thingy over here. So the height will be, so this is a hypotenuse and this is the opposite side. So we need to figure out the opposite side. So we'll use sine of 180 minus theta. 180 minus theta is sine theta itself. Okay. So is this clear? I hope that is clear. The diagram is important. Take a second, have a look. Now, I can figure out, therefore, the area swept, by R is equal to A half into base into delta R. Not vector form. Let me just write delta R sine theta. But this in the form of a cross product. So we can tell the area as a vector will be R times, crossed with delta R. So the direction of A, it will be determined by right hand rule. Okay. So as per this, what we have here is, just a second, R is there, V is here. So positive Z axis for this particular case, not always. Now, all this is well and good. So how is that we are linking to angular momentum? So we have to go to that. We'll start with delta R. So next step is to substitute delta R is equal to V delta T. And therefore, you have your area to be equal to half times the R V delta T. Okay, then we'll talk about if P is the linear momentum of the particle. So then what do we have? Then we have V is equal to, or P is equal to m times of V, or V is equal to P by m, right? And this I'll substitute in 1. Substitute V in 1. So can you see where we're going? So then we have delta A is equal to half times the R P by M delta T. Then what can I do? I can shift delta T. Can I write it here itself? I can shift delta T to the left side. You have mass that is constant over here and R crossed with P. And what is this? Yes, that's what we are trying to relate. The area being related to your angular momentum finally. Okay. So, or you can rewrite this as L is equal to 2m dA by dt. So, let me go to the conclusion part. So, geometrically, the angular momentum of a particle is equal to twice the product of its mass and the area swept out by its position vector per unit time. Right? If I rearrange this, I have L is equal to 2m times of A by T. So this is area being covered per unit time, right? It looks like tau. That's L, by the way. So this is what I'm talking about over here. This area swept, the sweeping rate, it's also known as areal vector, is half the quotient of the particle's linear momentum by its mass. So I'm just restating whatever the math is coming out here. So basically, if I happen to have a diagram, what all of this means is I can figure out the area, divide that with the rate at which this area was covered, and the mass, and by 2 as well. All of those, whatever division we are looking at, sorry, multiplication. 2m is multiplied and delta A is divided by delta T. So basically, per second, how much area is being covered, multiply that with the mass, 2 times the mass, and this will give us our angular momentum. So this will be connected in the next video to planetary motion. Okay. So for now, you guys can start with this heading, the basic idea, and the math from here. And by the way, theta is in same direction of V, delta R is same direction of V. So I'm able to mark theta over here. So I define theta to be angle between R and V. For a small time period, delta R will be equal to V and stuff. So I'm able to mark theta over here itself. So both V and delta R points in the same direction is what I'm trying to tell. And this. And this. And finally, the conclusion.